Okay, good morning, everyone. Good morning, Stockholm. Good morning, Durham. For those of you in Stockholm, if we're not quite as lively as usual, it's because our athletic team went down to an inglorious defeat last night. So we are in mourning, but we're going to try to focus on aeroelasticity, and that will bring us back into a more positive frame of mind. I want to do several things. I want to talk a little bit about homework number 6, which I know you're hard at work on. But even before I do that, someone the other day asked, are we going to ever talk about anything that's other than an aerospace application? And are there topics in aeroelasticity or fluid structure interaction that we're not going to cover in this course? The answer is there are a bunch of them. So I'm going to give you a few examples. There is a distinguished faculty member at McGill University in Montreal that is based in Cambridge, England. As the last name suggests, he's really from Greece, Michael Paidousis. And Professor Paidousis has spent a very long and distinguished career looking at slender structures and axial flow. So it's fluid structure interaction, but it's the prototypical problem that he's looked at is flow through a pipe. And sometimes irreverently referred to as the garden hose problem. Because his PhD advisor at Cambridge, who's a fellow named Brooke Benjamin, I missed the initial T, and then Brooke Benjamin. I'm not sure what the T stands for. Anyway, he was called Brooke Benjamin. He literally, and this is the classic amateur English approach to science and engineering, he literally went out in his garden, it is said, and took his garden hose and let water run through it. And it was sufficiently flexible that it would go into a flutter oscillation. And of course, it depended on how close to the end of the hose he held it. Right? If it was a short hose, it would flutter because it would flex one up. So if you, and then of course you could hold it up and do gravity, right? But you might try this. If you have a garden hose, you can do the garden hose experiment. Anyway, Professor Paidousis from there spent the rest of his life looking at that problem and various other variations on that problem. And for example, the early math model was a beam. It's a hollow beam, right? So you call it as a beam with a certain eon. And then you use what's called slender body theory for aerodynamics, which I'll discuss briefly. Which turns out to be a fairly simple, relatively simple aerodynamic theory. But then you can do all sorts of other things. For example, you can replace the beam model with the shell model, where you allow variations around the circumference in terms of deformation as well as along the garden hose. And you can replace slender body theory with a full three-dimensional fluid set of equations, either using potential flow models, which we'll talk about later. So you can spend the next several decades working on this, and he did, along with the whole question. He must have graduated, I don't know, dozens of students, all of whom more or less worked on this kind of issue. This is volume 1, and he references some of the classical literature, and he referenced some of my favorites. But if this volume, which is a fairly substantial thing, is not sufficient to your needs, there's a volume 2, which is even thicker. And these are relatively recent. This is volume 2. When was it published? It was published in, well, not that recycled, it's more recent. Volume 2 came out in 2004, and volume 1 came out in 1998. Okay. So, if you'd like to know about the garden hose problem, which is also, again, a fuel line, right? A fuel line. And particularly a connecting hose between two airplanes. It is an aerospace application, right? But they're refueling an airplane. And those project because they infer found it can be solved irregularly. Well, well, almost every aerospace project of any size goes on longer than planned and is substantially project. In fact, I had a friend who was an advisor in the Department of Defense, and he said, well, what you do is you take the estimate, the original estimate of the cost and time, and you multiply by pi. Otherwise, you can use 3 as a good approximation. So you multiply by pi, and you get an answer that's much closer to the final cost and the final amount of time it takes. And he actually had some data. He had a plot of original estimates on one axis and final cost on the other axis. Yeah, pretty much slope of pi, yeah. Okay. This is a book which I like since I wrote it. It's not the text in the course. This is the first book I wrote. And so there's a whole raft of people who work on aeroelasticity that folks can show. And again, this could be a tone, right? It could be a shell like his shell. That's why some of my papers are dark and some of the other ones. It could be some blood flowing through an artery. But the fundamental physics is somewhat similar. This book of mine has great advantages. On the other hand, the material is much denser. So I don't guarantee that it would take less time for you to read and understand this book. All right. Is that enough of that? But there are other books. There's a book by John Cooper and company in Bristol. He's basically a structural engineer who knows a little aerodynamics. And then there's a book by Dewey Hodges at Georgia Tech, similar sort of thing. Those books have very rudimentary discussions of aerodynamics. So there's, as you might expect in a field like fluid-structure interaction, there are people in the field who mainly know structures and a little bit about aerodynamics. And there are people who know a lot about aerodynamics and a little bit about structure. It turns out, and I say this as someone who has a balanced book, right? It turns out the aerodynamics are usually the harder part, as you'll discover when we get to the end of the course. They're certainly harder mathematically. I'll leave it at that. Okay. Now let's talk about homework number 6. Oh, questions. Any questions here in Durham, North Carolina? Any questions in Stockholm? Hearing none. Moving right along. So today is 20. Just 20. No, that's right. 18th was Tuesday. Okay, we're showing. The next week we're going in February, right? Okay, so we're just 20. Lots of 2s today. Okay, homework number 6. This is reversal analysis using Rayleigh-Ritz. I would say 90%, maybe 99% of all fluid structure interaction analysis is done using Rayleigh-Ritz. It's in industry, but even in industry. So it's working on it. So what do we do in Rayleigh-Ritz? First of all, and in the context of your homework problem, you take alpha, which is a function of y. I guess since it's static, it's just a function of y. And you write this as a series where you have some unknown coefficients, which you hope to determine, times some functions of y. And the homework problem, we chose these functions of y at my suggestion to be sine of 2n minus 1 over 2 pi y over L, right? So what do we do in Rayleigh-Ritz? milliliters is, for example, we write down potential energy, which is 1/2 the integral from 0 to L from Gj d alpha dy squared dy. Right? Now, I'm not going to do the details, and then I'll let you do that. But I want to point out a couple of things. If we take equation 1 and put it in equation 2, after a little bit of algebra, we get U is equal to 1/2 the double sum, not single sum, double sum over M and N of some coefficients, A sub M, A sub M, A sub N. Okay? It's a double sum. Why? Because it's quadratic in alpha. That's why it's a double sum. If this were cubic in alpha, it'd be a triple sum. So forth and so on. Okay. Now, what is the case of MM? Well, you're supposed to work that out in detail, but if you work on this a little bit, you see it's the integral from 0 to L of Gj, which itself might depend on y, right? Times dCm dy, dCm dy, dy. That's what it is. It's a constant, right? For a given Gj and some choice of these motions. In a similar fashion, and not going to go through the details, but I'm going to write it down, in general form, you're going to work out the expression for virtual work. And when you do that, you're going to be able to write it as the summation over M of Q sub M delta A sub M. It will turn out that these Q sub M's themselves depend on the A's, right? In fact, you'll be able to show that Q sub M is equal to the summation over N of some coefficients. I'll call it Q sub MM times A sub N. So it sort of has a quadratic form too. Okay. Now, why do I want to do all this? Well, because in the rate-of-this method, I take some modal expression, put it into energy and work. And if we were doing dynamics, we'd also put it into kinetic energy. But we're not here, we're just doing statics. And then we're going to use essentially Lagrange's equations, which you all have told me you understand in great depth and have a deep affection for, right? And what are Lagrange's equations? Well, the general form, including kinetic energy, is T minus U, right? If I'm doing statics, I don't have T. And then the Lagrange equations are d dt of the partial of L. In this case, I'm going to write this suggestively with respect to A sub I dot. So I'm using I here and not N and not M. Okay? That's important, as it turns out. Minus partial of L with respect to A sub I equals capital Q sub I. That's this coefficient, which itself in turn will involve the sum, right? But that's the recipe. That's the recipe. Now, you're going to, in your case, because it's statics, you don't need T yet. When we do flutter, you'll need T, right? For dual test response, you'll need T. But you don't need that yet. You'll also need U. And of course, you'll need the virtual work and these capital Q's, which are usually called generalized forces. You can call them anything you like, but most of them are also generalized forces. So, let me stop here and pause. Is that okay? So forth. Stockholm, are you still happy with it?
How is the QI, how does that come into play? How is it related to QN?
Well, QI is equal to QM if I equals M, otherwise it's not. I, M, and N are just indices, they're integers, right? Running over the number of terms I decide to select here. So if there's 17 terms, you don't need 17 at home. Probably need 2 or 3 of those. But So, but it turns out for the purposes of using this machinery, I sometimes want to distinguish between two different indices. In fact, I'll give you an example of that in just a moment. And so, in this case, I is some particular ace of I that I really find fascinating. It's not any old ace of I. It's just that one. Whereas when I'm summing over M and N, I'm summing over all the A's, right? And if I have a double sum, if I have a quadratic form, then I need two different indices so I won't miss any terms, right? If I just sum over, it's just one sum. If I assume, for example, that M equals N, only, then I might miss something. Does that help? Yeah. So,
we need to take into account also the reflection of the control surface, right?
Yes, we do. But not in the kinetic, not in the potential energy delta, and then do the virtual work, right?
Okay, so we have to devise an equation for the delta as function of alpha, and then we decide if it should work.
Well, let's go on. First of all, this L is Lagrangian, right? Never, ever to be confused with lift. But to get the virtual work, I need to think about lift and how it's related to alpha and how it's related to delta. So delta is going to come into play through its contribution to the lift. And the lift, in turn, is going to contribute to the virtual work, and that eventually will give you something that will allow you to do these Q's of M, or in detail, the Q's of M.
So would that be a constant term for all the simulation, or would that be for
which term are we thinking about?
the estimation of
These, in general, each of these Q's is going to be different.
yeah, but like the contribution of the deflection of the control surface delta. Would that be constant?
That will also be different.
So basically we need to find delta as a function of alpha. And that's
But the other way around. You're going to find these A's as a function of delta. This machinery is going to allow you to compute the A's as a function of delta. Once you know the A's, then you know alpha. Once you know alpha and delta, you can compute the lift, and then you can, and the lift per unit span, and just as you did in the previous homework, you can integrate over y and determine the total lift, and that will then be expressed entirely in terms of something times delta, because I know alpha in terms of delta, and since it's a linear model, I know alpha is proportional to delta, and I know each one of these A's will be proportional to delta, and then I'm going to end up, as I did in the previous homework, with something times the total lift is equal to something times delta. That something involves the dynamic pressure plus parameters, and then I'm going to find what dynamic pressure makes that whole coefficient. So the total lift in terms of delta equals to 0. And you should get the same number you got from the previous homework. If you don't, then something went wrong.
So is it independent of delta then?
Yeah. Within the framework of a linear model, reversal doesn't depend on delta. Now, if you include some nonlinearities in the model, as is done by Professor Boyle, I showed a paper like that. It turns out that in a nonlinear model, the reversal of dynamic pressure changes with the amplitude of the control surface. So it should be with the amplitude of the control, the magnitude of the control surface rotation. But within the framework of linear theory, the reversal Q is the same whatever, in this model, whatever the control surface is. The first is the control surface rotation is large enough that all can sound. Okay? All right. I'm going to show you one more thing, and then two things, actually. Remember, I have this case of the MN is equal to the integral from 0 to L through Gj e alpha m dy e alpha m dy dy. Okay? And in the homework, you're going to do two cases. You're going to do the case where Gj is a constant. And you're going to do the case where Gj is some reference value, which times 1 minus y over L. And when y is 0, Gj is equal to reference value, which just tells you that Gj references the Gj torsional stiffness at the root, right? But where the wings clamp at the fuselage of the wind tunnel wall. It will turn out, because I have given you some very nice functions, case of Mn will be 0 for M not equal to N if Gj is equal to a constant. This is a property which is beloved by those of us who do this sort of thing for a living. It's called orthogonality. Okay? There's an orthogonality of these modes with respect to their contribution to case of Mn. It turns out, for the case where Gj is not a constant, there are some other modes, not the ones I've given you for the homework. There's some other modes which are also orthogonal. But finding those modes is really hard compared to finding the modes for Gj is a constant. Therefore, when you do something that Gj is not constant, normally you use these modes, the simple modes, right, which are orthogonal for the case when Gj is a constant. But case of Mn is not 0 for any, well, M not equal to N, if Gj depends on Y. And when you do the calculation, you'll see that. Right? So when you do the calculation, you find these cases of N, but many of them found to be 0 for the first case, when Gj is constant, don't be too surprised. Be happy about that. What that means in practice is, well, I won't say what it means in practice. I'll tell you. Okay, the other thing I want to point out to you is the following. Remember now, the U is going to be like this. It's going to be K sub Mn, Q sub M, oh, not Q, we're using A, sorry. A sub M, A sub M. Now I want to differentiate this with respect to AI. Okay? Because that's what appears in Lagrange's equation. And now you'll see why I wanted to use all these many different subscripts. Because if I don't use all these many different subscripts, I might get confused. You probably wouldn't, but I would. Okay. So if I differentiate this U with respect to A sub I, what does that mean? And if you want to, you can be very particular. You can set I equals some particular number. But it doesn't matter, because once you see how it works for one particular number, it's a similar sort of thing. So let's take I equals. What in I do you like? 1. You like 1. Okay, let's do 1. Okay. So we're going to take partial U with respect to A sub 1. And we're going to use this equation. I'll call this equation 3. I'm going to use equation 3. I'm going to differentiate it. Okay. First of all, I have 1/2. I have a double sum. A sub 1 appears here. It also appears here. So there are going to be two terms. It's a product rule, right? There are going to be two terms. There's going to be one term associated with M equal to 1 from this differentiation. There's going to be another term when N equals 1. Okay? Okay, so I'm going to get, let's consider first M equals 1. Then I'm going to get summation now over N alone, K sub Mn times A sub N, except M is equal to 1. Okay? But then But then I have another term. I have a summation over M of K sub M1 times A sub M. Okay? Right? That's what I get. But if k sub m equals k sub n m, if I reverse the order of the indices, then these two summations are exactly the same, right? Because n is just a bookkeeping. It's an accounting device, right? Once I have a single sum, I can call this n m if I want to, or this m n if I want to, right? And if it turns out that k sub 1n equals k sub n1, and more generally this is true, then these two summations are exactly the same thing, which is nice because then I only need a single summation and I can cancel out the twos and I'm done, right? So if this is true, then partial of u with respect to a sub 1 is equal to the sum over n, or I can make the sum over m, doesn't matter. K sub 1n k sub n. Right? Or I could write this also k sub n1, right, since they're the same, if this is true. Is this true, by the way? Well, sure it is. How do I know that? Well, I go back up here, look at it. If I interchange n, m, and n, I get the same answer. So by looking at my definition, I know it's true, right? So once I know this is true, then I know how to differentiate it. This is for a sub 1. Well, what if I have a sub I? Well, I just replaced 1 by I, and now it's true for any mode. It would be true for a sub 2, a sub 3, a sub 4, right? Then this will help you, I hope, when you do the homework. Questions? Yes.
For the final part, I don't get why do you want to calculate the du over dAi?
Why do I want to do that?
Yeah.
Because I want to use the process equations. I want to use this equation to compute a relationship between the A's and delta. Okay. Because once I do this, once I do all of this methodology, this set of equations will give me, for each, as many modes as I have, say I equals 1, 2, maybe 3 even, I'll end up with 3 equations to determine a sub 1, a sub 2, and a sub 3 in terms of delta. Then it will be 3 linear algebraic equations. If I only use one term, which I would suggest you start with, that would be pretty easy to work with. Even with 2 terms, I can probably do 2 equations and 2 unknowns by hand. With 3 terms, you might want to write a little matrix code to convert a matrix and find the A's in terms of delta. And then once I do that, then I'm going through. Remember what you're going to do ultimately. You're going to find a sub 1, a sub 2, and as many A's as you have in terms of delta. Okay? Once you know that, then you know the lift per unit span is Q, C, DCL, D alpha times alpha plus DCL, D delta times delta. But the alpha, you know, is A1 times V1 plus A2 times V2 plus A3 times V3, right? And then you're going to integrate, right? You're going to integrate this to get what I'll call total lift. And that will turn out to be proportional to delta because the A's are proportional to delta. So everything is proportional to delta. And what will appear in all of this will be the dynamic pressure. Now, once you have this in numerical form, remember you're trying to find the Q that makes this total lift 0. You may want to plot the total lift. Once you have it in numerical form, you may want to plot the total lift versus Q and find out at what Q does this become 0. I don't think you will be able to do it analytically as you did in the previous one. I think you'll actually have to do some numerical. But that's good. Because that's what happens in real life. Particularly for the case when GJ is not a constant. Remember, in the previous homework, we very carefully made GJ a constant so we could solve the difference equation, have limits and all that. Once GJ is not a constant, that avenue, that solution or approach is no longer available to you. And you have to do something like this. But it's not impossible. It's just more work.
I have a question about the kinematics. When do we know that K and M is equal to K and M? Yes, it depends on your shape, the shape function you choose, right?
It depends on the
shape function.
No, not really, because it would be true for any shape function. This alpha m is the same function as alpha n when m equals n, right? So these are the same functions. So any function I would use, as long as I was consistent, Kmn would be equal to Knn. You can't avoid that. Now, what is special is sometimes these coefficients are 0 when n does not equal n. Right? That's orthogonal. And that's true, as it turns out, for the special case where GJ is a constant. For the mode shapes that I gave you, there's other mode shapes one could use, for which this would not be true. This orthogonality probably would not be true, even when you have GJ as a constant. But normally what we do in these kinds of problems is we find some nice functions with a good orthogonality property. And frequently that's a simpler structure with constant property. So we look at the constant property structure to find these wonderful functions. And then when we do something that doesn't have constant property, we continue to use those functions. We still have the symmetry property, but no longer have the orthogonality property. Okay? Stockholm, any questions there? I do not hear you. Okay. Let me say one other thing, because sometimes in the literature you may encounter this other method, and we discussed it briefly earlier in the class. So let's talk about the Glurkin method. Occasionally someone will say, I'm going to use the Glurkin method. I prefer that to Rayleigh-Ritz. I'm not sure why they would do that. Although, there are times when I actually do it myself. Not very often. Occasionally I slip. Sometimes you get the same answer, and sometimes you don't. The Rayleigh-Ritz method, if you apply it properly, always gives you the right answer. The Glurkin method may or may not. And the distinction is, if I do the Glurkin method, I have to make sure that I choose functions in my expansion that satisfy all the boundaries. If I don't, I'm not going to get the right answer. I may get something that's not terrible, but I won't get the right answer. Whereas with Rayleigh-Ritz, all I need to do is choose functions which satisfy the so-called geometric constraint. In our case, our example, I mean to twist it y equals 0 is 0. But I don't have to satisfy, in the Rayleigh-Ritz method, strictly speaking, I don't have to satisfy the bound condition at the free end where Gj times d alpha dy is 0. I really don't have to do that. Now, it turns out the functions I gave with Homer satisfy all the bound conditions. So if I use the Glurkin method with those functions, I should get the same answer as with Rayleigh-Ritz. Okay? So let me briefly describe how the Glurkin method works. If you want to, perhaps for credit, you can do Glurkin too. But you should not only get the same answer, you should get the same equations for A1, A2, A3 in terms of delta. Right? So you don't even need to do numerics. You just need to write down the equations. So hang out those are the same equations I got using radius. Okay. In the Lagrange method, we do the following. We start with the differential equation. And for our example, it's gj d dy of gj d alpha dy plus QCE DCL d alpha times alpha plus DCL d delta times delta plus QC squared CMAC naught, which I'm going to have you set to 0 to simplify things a little bit, plus DCMAC d delta times delta equal 0, right? That's the differential equation. Where did that differential equation come from? Well, rigorously it comes from the principle of virtual growth. So, if you go back to the principle of virtual growth, or dynamically speaking, Hamilton's principle, you know, that's the thing. Rayleigh-Ritz and America all really can be traced back to the principle of virtual growth. But sometimes people prefer to do this. Start with a difference equation. Write alpha, a function of y, is a sub n times v sub n of y. And we put that in this equation. Let's see. Where am I on equation numbers? I think I'm on equation. I'll call this equation 4. Okay? So I can put this in here. Okay? And when I do that, I will have however many A's I have. Let's say 17. But I put this in here, and now I have the following. I have one equation of 17 unknowns. That is not a good situation. Okay? I need 17 equations. Okay? So Galerkin said that I get 17 equations the following way. And I'll do them one at a time. Well, I'm not going to do all 17. I'll just do one equation. And following the earlier suggestion, I'm going to find an equation by the following technique. I'm going to multiply, once I make the substitution, I'm going to multiply the result by phi sub 1, the first mode in this series, and integrate 0 to L dy. Okay? That's what I'm going to do. Well, and then I use phi sub 2 and phi 17. Now I have 17 equations, 17 and 9. Those equations, if the phi satisfy all the boundary conditions, will be exactly the same thing you got from Rayleigh-Ritz. Okay. The Galerkin method was developed quite independently from Rayleigh-Ritz. In fact, I think the Galerkin method was actually developed earlier, I think. But don't hold me to that. Okay? So sometimes you hear people talk about the Galerkin. But the Galerkin and Rayleigh-Ritz are related, but they're not always exactly the same. In the particular homework example you're doing, they should give you the same equations and therefore the same answer. Okay. I think that's all I'm going to tell you about homework 3 and 6. Does that inspire you to go forth and do great things? Good. I'm happy for it. All right. We're going to use Rayleigh-Ritz a fair amount. And in particular, we're going to use Rayleigh-Ritz to do flutter analysis and also gust response analysis. In fact, you remember after you do homework 6 and the homework 7, you're going to use Rayleigh-Ritz again. You could use Galerkin's method to do flutter analysis, but then you do have to be careful about the mode shapes. In fact, the mode shapes I gave you for the flutter analysis, if you look at that, don't satisfy all the boundary conditions. They just satisfy the ones at the group. They don't satisfy the ones at the fit. Okay. Are we ready to press on? All right. So let's talk a little bit about, since you're going to do a homework on flutter and become an expert on that, let me talk a little bit about gust response. Okay. Or if you're a turbine machinery person, we would call this inlet distortion. If you were looking at blood flow through the artery, this would be computing the deformation of the wall due to turbulence in the flow. So the turbulence would have a mean steady flow component, but then there would be a random fluctuating component about that mean. And if you wanted to know how the artery wall responded to that random fluctuation of the fluid, we'd have to do something like what I'm going to talk about. But let's start with an aerospace example. And let's do the way. We could do the typical sector the way this is. So let's see, we're on page 5. And we're going to do the wing. And we have a mean flow, U. But now we also, and this acts in the, U is in the X direction. So I'm going to write this way. I'm going to think of the velocity now being a vector. And the big component in the X direction, which has a unit vector I, right, is in the X direction. But then it has another component, I'm going to call it W, never to be confused with the section of the plate. But I'll put it as a G on it so you'll know it's really the gas velocity component. And that's in what I'll call the K direction, where K is normal, K is the unit vector normal perpendicular to the wing. Right? So now if I look at, if I take a side, this is sort of a top view of the wing. Now, if I look at a side view, here's mine. I'm looking at the second wing right now. But now I've got a U component this way of the flow, but I've got a WG component this way. Right? So now the total flow velocity vector is no longer aligned with the undeformed chord of the wing. It now is at an angle, right? It's at an angle. And that gives rise to what is usually called as the effective gust angle effect, which is just WG over U. Okay. So when I want to do a gust analysis, the simplest version of gust analysis, if I have my aerodynamic, this is now lift, not be confused with Lagrange ever, right? This is lift. QC DCL D alpha. Now I write this alpha. Alpha is the twist that the wing may undergo, plus another contribution to alpha associated with that. Right? Well, you always have to worry about plus or minus, but in fact, it's fluctuating about some average, so you don't really care about the sign because you're really in the magnitude of the response. Yeah. Depending on your sign convention, there's fluctuations, and different authors use different signs. In fact, I think the usual sign convention is actually WG is positive downward, which makes which allows you to use the plus sign. For the same reason we chose H to be positive down, right? Basically the same thing. Okay. So now the thing is though that usually this is a function of time. Gust response is a dynamic phenomenon. But you can look at certain special cases. You can look at step changes in the gust responses, a so-called sharp-edge gust. You can assume that the gust velocity is a sinusoidal function of time, which makes the algebra a little easier than the famous model as well. Or you can let WG be a random function of time. There's a whole methodology and machinery associated with treating the gust as a random function of time, and then you try to compute the random response, and so we need to talk about that. Now, I need to ask you a question. If I told you, if I have a linear model, and I look at a sinusoidal function of time for the gust line, and I find the sinusoidal response in terms of alpha or plunge or whatever, then with a little bit of mathematics, I can find the solution for any arbitrary time history of WG and the corresponding arbitrary time history of the response. Would you believe that? Why would you believe that? What allows me to do that? Fourier analysis. That's right. Fourier analysis. So let's briefly go through that. Let's assume WG is some magnitude EI omega t, where omega is the frequency of the gust. And if I could make it omega sub g, but I prefer not to have to carry along that subscript of that. If I do that, then let's say I want to know alpha, or if I'm looking at not just the torsion of the wing, but also the bending of the wing in terms of h, then because if I have a linear model, then both of these must be also go like EI magnitude, right? There's some amplitude. Now I have equations of motion. Once I put this in and this in, these equations of motion, which are in the time domain, become no longer difference equations in the time domain. They become algebraic equations in the frequency domain. And then I can find, because it's a linear model, I can find the ratio of h bar over WG bar and alpha bar over WG bar, right? And because it's a linear model, h and alpha are proportional to WG, so those ratios are independent of the magnitude of motion. And this is such a nice feature. These ratios are given a name. They're called transfer functions. And people, for the most part, focus on the fact that these transfer functions now depend on those frequencies. Okay. Okay. And it depends on frequency, which we want. So these transfer functions. Well, let me just deal with alpha for example. Alpha bar over G bar is some function of frequency, right? As well as parameters, including dynamic pressure, right? As well as all the other parameters that are in my mind. Okay. Now, if I go to equations of motion for this wing, which I explain with something like this. Okay, doing the wing, so I better put it in this way. Second partial of y EI, second partial of h with respect to y equals minus L. And there's another equation which I won't bother right now for involving alpha. Fourier transforms, if I believe in Fourier transforms, mean the following. I can define, I'll call it the transform of h, as the integral from minus infinity to plus infinity of h of t e to the minus I omega t. This is the definition. Oops, sorry, I went off the page. Thank you. This is the definition of a Fourier transform. Okay, but I want to transform this equation. Okay, and therefore I need also the transform of H double dot E minus I omega t dt. And with a little bit of analysis, that some of you have seen before apparently and others may not, I can show that this is equal to I omega squared integral from minus infinity to infinity of H of t E minus I omega t dt. But that, of course, is just the Fourier transform of H. The point is that when I look at this equation, if I do what I'll call the simplest thing, which is just assume that H and alpha are sinusoidal functions of time, I'll get these wonderful factors, I omega each time I have a time derivative. But if I think of this in a more general context as taking a Fourier transform, I get the same equation. So the sinusoidal input-output relationships are also the relationships I get from taking a Fourier transform. What's the advantage of that? Well, because then I can solve for H bar, alpha bar, as Fourier transforms. And then once I have the Fourier transforms, if I have taken the course in Fourier transform theory, I know how to invert. If I really want to find H of t, and I now have computed H bar, it's 1 over 2 pi, the integral from minus infinity to plus infinity of H bar of omega, e to the plus I omega t, d omega. Oops, sorry about that. D omega. And I'm done. So if I have linear equations, I almost want to do the frequency domain analysis first, because then I'm dealing with algebraic equations. But then at the end of the day, once I have that answer, I can always go back and find the answer in the time domain. And Jim has become famous and notorious for doing a lot of things in the frequency domain. And I'm thinking here in terms of what I'll call structural equation functions. But you can do the same thing for the aerodynamic equations, which we did not discuss, right? At least not in detail. And it turns out that while it's not only easier to solve the structural equations using the sinusoidal inputs and sinusoidal outputs, that's especially true for the aerodynamic equations. They're far easier solve for that special case. But in principle, once I do that, then I can always find the general case using transform. Now, how many people know about Fourier transforms? Oh, that's good. I'm trying to remember the difference between the Fourier and the Laplace. I tell you that without any extra charge. Okay. The good news is the Laplace case is a special case of the Fourier case. If, in fact, for example, here we define, this is the definition of Fourier transform, this interval from minus infinity to plus infinity, CD. If I think of nothing happening before some particular instant in time, which I, by definition, call time t equals 0, that's all I do. And then usually in the Laplace transform world, rather than dealing with omega, you deal with another variable, maybe you want to call it P, call it the Laplace variable, which by definition is I times omega. So there's a change in notation, and this lower limit is now going to be 0. Most of the useful input-output relationships are really best defined, best derived, and best obtained by using Fourier Transforms. But then you say, oh, but really nothing's happening for big material, and then you can take advantage of that when you actually use it in there. So Laplace is just a special case. Okay. Now, for those of you who know about Fourier Transforms, you might want to read my little account in Chapter 3. I have a nice discussion. Normally what you do when you develop this, you start with sinusoidal input, output, and then you look at periodic and time inputs and outputs, because a periodic input-output relation can be expressed in terms of a Fourier series. But now periodic means over some interval of time, things repeat, right? But then you take the limit as the period of the periodic input-output goes to infinity, and when you do that, you get a Fourier integral. Because the Fourier integral assumes that things have gone on forever. They've gone on from minus infinity to plus infinity. That's all time, right? That's the whole thing. That includes everything. Now, one final thing, but I don't think I'll take time to do it today. But let me ask you this question. Oh, let me ask my friends in Stockholm. Are you okay with Fourier Transforms and Fourier series, and you'd be happy to read Chapter 3 and refresh your memory about that? Maybe they're too disturbing to respond. Okay.
Yeah, we think we combined together.
Did he say he was okay? Sorry. Okay. Well, read Chapter 3 about Fourier series and Fourier transforms. One final comment, and so I think we'll save that for another day. The nice thing about Fourier transforms as well is there's a whole machinery associated with random inputs and random outputs. Okay? And it usually goes by the phrase power spectral density analysis. So how many people know about power spectral density analysis? Sort of. Yeah. Okay. Well,
Just pretty much like just because the frequency that mean is different.
yeah. Once I develop the machinery of Fourier transforms, then I can, in principle, take all this and put any arbitrary time history in, and then compute an arbitrary time history out. But if you really have a random input, that's tedious, because you have a random input, you probably want to keep repeating it for a number of statistically significant time histories, input and output, and then do averages and so forth. So often what you really want to know is if my gut has a certain mean velocity and it has a certain RMS fluctuation about that, what is the mean of the response of the aircraft or whatever the system is, and what is the RMS response about that, right? That's what you really want to know. And it turns out there's a whole theory associated with power spectral density analysis, which allows you to do that and avoid any computations in the time domain whatsoever. So if all I want to know is the time average of the output to a time average of the input, and the RMS fluctuation of the response about that time average to an RMS fluctuation of the input, then I can stay with the frequency though. Okay? Okay. All right. But I think I'll save the discussion another day. Any questions about what we've covered so far today? We covered quite a bit. So you're making amazing progress. I hope you think this. Stockholm, very nice to see you today, albeit at a distance. And we'll see you again on next Tuesday.